Welcome back. I hope you have had a good coffee break. So this morning we had a fantastic talk of Stefan, and we learned about a real application, machine learning in real industrial application. So, and we also learned about reduced order modeling, control theory, and so on. So what is missing is what do we do if we want to control a complex, nonlinear, high-dimensional system like turbulence, and we have, say, 10 actuators, 10 sensors, and what should be our strategies for optimizing a control goal? And this is what I will talk about today, and I will use my usual path. So first I will come from human understanding, so model-based control, and then I will go to completely self-learning control. And we will learn from the wisdom of the eagle, which Steve has already introduced. So essentially we will try to imitate a bit the nature's way of learning. And this is based on collaborative work with Guy, sitting over there, with Nang, Luc, François, Van de Wey, Yujo, and again, Marek, Steve, and Ulrika. So first, I will introduce you to the applications of turbulence control. Then I will demonstrate you in one example benefits of feedback control. I will show you in the next example how far you can go with model-based control, high lift configuration with a two-frequency dynamic. And then we will go learn a new method, machine learning control, which conquers the nonlinear jungle, and we apply to distributed actuation in a turbulent jet, and a couple of other things. And for those of you who do not have experiments, but CFD, I will offer a poor man's version, cluster-based control, with a corresponding example. My lecture will end with a summary and with a quick demonstration of our machine learning control package, which you can download from the web page. Motivation. So we have seen already some nice motivation this morning. Another motivation is a car, control strategies for drag reduction. So if you want to reduce the drag for lowering the fuel consumption and so on, the first choice which you would take is aerodynamic design. So here you see a car, a concept car of Renault, obviously very aerodynamically designed. Where can you see that? What is aerodynamic about the car? Yes, good. What else? Oh, look at the wheels. It has very small gaps. So this is one thing. Look at the bottom. It has a diffuser. So the wake is reduced. And now the question is, what could we do more on this car to reduce the drag even further? Well, we can build some actuators at the trailing edge over there. Is there a pointer? Any pointer? Okay. So we could make some actuation here at this trailing edge. We could blow, or we could suck, or we could do multi-frequency forcing. Here we can do it blindly, but of course the best is if we include the flow state, so if we do some closed loop control. So this is where we have the largest opportunities. And actually, a lot of these things have been done. If you go to a magazine called Research and Development in 2004, you see this car, and you see here the simulation with an experiment with a actuation off. So the wake has a certain shape. So now you have zero net mass flux blowing here. There's a change in the wake structures. What is most important, you gain something like 20% drag reduction at 90 kilometers per hour. This translates to about 1 liter of fuel savings on 100 kilometer, and they claim it only took 10 watts of actuation energy. Sounds very good. But then we should see it at the cars, right? If it's that good. Any idea why we don't see it on the cars? But the answer is the solution is too expensive. So they've figured out it would cost the customer something like 3,000 euros, and none of the customers would invest this for these savings. Now there are a myriad of other applications. You have seen these examples already in Steve's talk. You can go from simple academic configurations to more practical ones, trains, cars, wind turbines, engines, and so on. So there are myriad of possibility of doing turbulence control and doing closed loop control. At the end, you will always have a dynamical system. So your plant, you want to reduce the cost. For instance, the drag, you have some perturbations into the physical system. So this is called real-world conditions. And you never know the full flow state. You only have some sensors, and you have to use the sensor knowledge to build a controller, and the controller drives the actuators. And there are several possibilities now. You can do open loop forcing. Very famous is periodic forcing. This is very frequently used. You can do closed loop control with sensor feedback, or you can do a combination of both. And you have seen this slide already, so I will give you more reasons to get inspired by this path, by the machine learning path. I want to show today that you can actually do the control optimization in the plant where you would not be able to do it with a model-based paradigm. So, Stefan, I'm sorry, I explained it already in my first talk. So now we benefits of closed loop control. In my first lecture, we have discussed the wake stabilization with a hot wire sensor here and a volume force here, and the controller was derived by some model, so by some three-dimensional model. And if you want to stabilize a flow, of course, you need feedback. You cannot stabilize a flow without feedback. Now the question is, isn't this a bit academic? What do you do in the experiment? Well, here we have an experiment. D-shaped body flows from left to right. The goal is to reduce the drag. You have a couple of 15 pressure gauges. You can blow and suck on both actuators independently. Reynolds number is around 40,000, so it's reasonably turbulent. And I'm reporting now about a PhD thesis which has been done some time ago by Marc Pastor. So the question is, how do we design the control from the sensor readings to the actuation? If we don't actuate, we find von Karman vortex shedding. This is a smoke visualization here. Here you see a vortex, and a vortex, these structures should not surprise you. If you have a vortex is a low pressure region, so the fluid particles spiral around, and in order to compensate for the centripetal force, you need a lower pressure inside. So if the vortex is close to the body, low pressure, and you get an extra drag. So one control strategy is to prevent the vortex shedding here and delay it. Now the question is, how can you possibly do this? One thing is, if you look at the vortex here, it's antisymmetric, so the u prime in this direction corresponds to the opposite u prime here. So maybe you should do symmetric forcing. And obviously the flow likes the harmonic frequency, so you should do something else. So you could take, for instance, golden section times the natural frequency to be maximally incommensurate. And it turns out this is a pretty good choice. Of course, you learn it in hindsight. So if you actuate with a frequency which is slightly lower than the natural frequency, then the flow stabilizes, and you get 40% increase in the base pressure, 20% decrease in the drag. So now you could say, I'm very happy with this open loop forcing. Where is the problem? Well, suppose, for instance, you would change the velocity a bit. Suppose, for instance, you would now decrease the velocity. Suddenly your actuation frequency, your physical actuation frequency becomes your natural frequency, and the drag increases again. So you have no robustness against change of your oncoming velocity. And so this is one of the reasons why we may want to use feedback. So in the next step, we do feedback control, phase control, something which is similar to what Scott was teaching. And now we get the same drag reduction, but now for all Reynolds numbers. So we can change the Reynolds numbers, and we still get this 20% drag reduction, and we also save on the actuation energy, 40% actuation energy. So now with every watt which we invest in the actuation energy, we gain 5 watts in the towing power. So this is energy, very energy efficient. By the way, you can also stabilize the wake with high frequency forcing, but then your energy investment would be significantly larger. So now there's one application where you cannot do anything with open loop control. Suppose, for instance, one of the actuators fails. You can only actuate on the lower side. So in this case, I can tell you open loop control will not work, and you need to do some type of closed loop control. You get the same drag reduction, the same energy, and again, this is not doable open loop. So this is a motivation why feedback maybe how feedback is beneficial for instance, a wake stabilization. So you came here also for some math, some equations. How can you treat these things on a more physics-based way? Well, you would typically start with a velocity field corresponding to the steady solution, and then you have a fluctuation. The fluctuation is harmonic. That means it can be spent by something like a cosine mode and a sine mode, so essentially two-dimensional approximation should be reasonably good enough. So we have seen now enough example of this case. The linear dynamic looks something like this. So these mode amplitudes behave like a growing oscillator, and you can actuate, and we can change, rotate the mode in such a way that we only affect the second oscillator. So this is single input control here. Now, how can we simplify things? We can now write things in polar coordinate and look at the growth rate, the natural growth rate corresponding with the linear dynamics, and you will quickly figure out this corresponds to that. And what does actuation do? The actuation is an extra term. So this one is a instability. So this one will always lead to the growth. So now you have to design your actuation in such a way that this is negative. How can it be negative? Very easy. If A2 is positive, then B must be negative. If A2 is negative, then B must be positive, and so on. So essentially, the sign of B should be opposite to A2. What we want to stabilize the dynamics, so we want to make sure that it decays exponentially fast. So essentially what we want, our controlled dynamics, controlled stabilized dynamics corresponds to this dynamics here. And now we would like to get a controller for this purpose. So a naive choice is the following. You take this equation here and invert it and solve it for B. Where's the problem? You divide by A2 and suddenly you get infinite control. Obviously, this is not a good choice. But you can go do something simpler. You can make the ansatz B equals, you make a linear ansatz with opposite sign. And now you can determine the gain such that the equation is satisfied in a one period averaged sense. And then you arrive at such a controller. You see here, if the more you want to stabilize, the larger the gain. The more unstable the flow, the larger the gain. The more effective the physical gain of the actuator, the smaller the gain. So this controller makes perfect sense. What I'm showing you here is called energy-based control. And the advantage is I've taught you this now in 3 minutes. So you don't need to go through the control theory textbooks. This is one advantage. So it's a very simple approach. There's another advantage, namely, since it's an energy-based approach, it also works for nonlinear settings. So we have used it for most of our approaches. So this is linear full state feedback. Here you see an example. So we choose some parameter, growth rate 0.1, frequency 1, gain equals 1. So the story is always like this. If a coefficient is not necessary, set it to 0. If it's supposed to be small, set it to 0.1. So G equals 1. And if we want a controlled growth rate which is opposite to the natural growth rate, then this implies that the gain should be 0.4. I could explain why, but I will not do so in the moment. In the dashed line, you see how things spiral outward, and at some point control kicks in, and now we spiral inward again. Control designed, finished. And you see it's a bit elliptic. Why is it elliptic? Because essentially you can only act in this direction. So when you are here, you have a strong gain, so you can significantly reduce the amplitude. If you are here, you can do nothing because your control has to be 0. So now we have a perfect understanding of linear control and a very simple method of doing so. Why is this of relevance for turbulence? So this is linear control theory. We have heard the exquisite talk of Scott. So there are a number of nice things you can do in addition, which energy-based control does not deliver. So you can guarantee optimality of the control, guarantee robustness. You can do state of the estimation from sensors, sensor-based control, and so on. So lots of nice things. Why is this in my lecture about turbulence control? Well, you have oscillatory coherent structures. You can have a dynamical model, a calibrated dynamical model for those. And at the end, you will always arrive at some phasor control for the dynamical system. So your control will always be the measured phase minus a difference, and then cosine, and then some gain. And you could also use empirical identification of the phasor gain. At the end, you only have two parameters in your control law. To some extent, you don't need the model. So the model comes as an ornament to your publication or to your understanding, however you see it. We have also talked about non-linearity. So there is one non-linearity associated with a Reynolds stress. The average flow does not stay as a steady solution. You move away. So we have seen it in my first talk. Now you decompose the velocity field in the steady solution, in the first harmonics, and in the mean field deformation. Again, first harmonics, mean field deformation. You get such a dynamical systems, which we have discussed earlier. So there is an oscillation where the growth rate is determined by A3. So A3 is the shift mode, it's a base flow variation, and this is proportional to the Reynolds stress. And so effectively, you have a locally linear dynamics which you can control. It will not surprise you that the control design works. Let's look at one solution. There's a periodic solution to this system, which is shown here. In weakly nonlinear stability theory, you say the growth rate is proportional to the Reynolds number difference to the critical Reynolds number. So the further you go away from the critical Reynolds number, the larger the growth rate. And at the end, you arrive at the Landau equations, which we did already in our first lecture. So you get a linear growth rate, cubic damping term. And in this setting, the growth rate is proportional to Reynolds number minus Reynolds crit, assuming a supercritical Hopf bifurcation, which you observe for the cylinder wake. So typically, you can relax this. So this is not really necessary. You can identify also a model even at high Reynolds numbers. I just mentioned it for completeness because there are a number of publications who do similar approximations from a stability perspective. So how can we design the control? very easy. We do the energy-based control. Then we get something like this. We get practically the same controller, except that the growth rate now is the natural growth rate minus the mean field bifurcation. So this arises if we take the local linear model. So this is a justification of the linear parameter varying control. And essentially what this equation says, if you are in the limit cycle, then this growth rate should be 0. That means your actuation should be lower. But if you want to go closer to the steady solution, then your gain must increase. Now there's a sweet spot. At some point you have stabilized the flow, and then also this A2 goes to 0. So initially you have to ramp up your control, and then you have to decrease your control to 0 after stabilization. So this is the situation again. So now A1, A2, we live on the mean field paraboloid, which we have seen already now a number of times. You spiral outwards. At the end, you end up on a limit cycle. And then we do our control. You see the red curve here. And then we move downwards back to the limit cycle. If you want, you can try these type of things. So control design is easy. Modeling is also easy. Again, why am I teaching it? Well, there are oscillatory coherent structures. The base flow modulation on the mean field have been frequently experimentally observed, and what we found in our collaborative research center for flow control, if you don't take into account the base flow variation, then your control may not work. So this is a critical enabler for control, and which is also increasingly realized in JFM publications. And we also can identify the mean field paraboloid from experimental data from turbulent flows, where you would not initially expect them. Good. Now we go to another configuration, closer to what Stefan was teaching, high lift configuration. So this is a old-fashioned design, 3 sleds. We want to increase the lift. For this, we can do blowing and suction here at this point. Our plant is a MK epsilon model, and we do a 2D unsteady runs, structured grid, and so on. The purpose of this exercise is to explain why high-frequency forcing mitigates or increases the lift and also reduces the drag. So this is reduced order modeling for understanding, which at a later time we also use for control. If you look at the unforced flow, you see these type of streamlines here. So there's some vortices. If you average, one vortex here persists. Of course, this is not good. And if you look now at the fluctuation, you see heavy vortex shedding here. This is not good. So I've flown once in a Lockheed 1011, and when it was landing, high lift configuration, I could really feel the vibration. So this must have happened there. If you do some periodic forcing with a frequency which is 80% larger, then you get a much more streamlined configuration. In the average, this is just a small fluctuation, and the fluctuation which remains is high frequency shear layers structures, which you see here. So here this gives rise to a 15% lift increase, and we would like to have a dynamical model explaining this. We have now 2 states. So there's one limit cycle corresponding to natural setting, which we can resolve with the POD modes without actuation. There's another limit cycle with the actuated flows. So these are 2 other POD modes which we use. The total fluctuation now has 4 POD modes, which you see here. And the base flow somehow has to respond to the strengths here and the strengths here. And as I will explain in a second, each of these Reynolds stresses from this fluctuation and this fluctuation changes the base flow. So we get 2 additional shift modes or 2 additional modes describing the base flow variation. So here you can have a forced transient from this limit cycle here or natural transient back. And this shall be described as such a dynamical system. And the fluctuation drives the base flow. So we derive the base flow effectively from the Reynolds equation. and the actuation is modeled essentially by the blowing and the suction here, and the derivative. The reason is the following: we want to have a cosine and sine signal, and we never know to which phase our actuation communicates. So this is a model at which we arrive with some mean field consideration. I ask you to believe it for a moment. So this is what you arrive if you do harmonic balances. If you look at the first, if you look at the harmonics, contribution of the harmonics of the natural shedding and actuated shedding, what you see here, a dynamical system with two oscillators, one oscillator here, one oscillator here, and the actuation on this side, and the actuation only affects the shear layer structures. And without forcing, this growth rate is positive, so vortex shedding will always want to occur. The shear layer vortices are always negative, so without forcing you would not see them. So you have a damped oscillator here, which you need to excite, and you have a forced oscillator, an unstable oscillator here, which you cannot directly affect, but somehow they seem to be communicating. How are they communicating? If you look at the growth rates here, you find that the growth rate of the unstable fluctuation has a positive value here. Then there's a component which gives rise to the cubic damping. So without actuation, this growth rate will go to 0 by this amplitude increasing. But if you actuate strong enough, you also mitigate the growth rate. So if this term is as large as the growth rate, then this growth rate becomes 0, and von Karman vortex shedding cannot exist. Of course, the frequency depend on both energy levels, the other growth rates, and so on. But this is the key equation which you need to keep in mind. And what this equation tells you, you excite one frequency, it changes the base flow, and by changing the base flow, it mitigates the linear system of the vortex shedding. This is an example of frequency crosstalk, which you would miss with any linearized approach. Any questions so far? Good. So this is a model. Of course, now I have to show you that the model is not only a fantasy. What we do, we fit our model to the U-runs that are here, A1, A2 from vortex shedding, A3, A4 from the shear layer structures. And we see here two transients. So there's one transient going from the limit cycle to the fixed point, and then one from the fixed point to the limit cycle. So one is a forced transient, and the other one is a natural transient. And here you have the opposite scenario. You start at the fixed point, then you go on the limit cycle under actuation. If you stop actuation, you go inwards. And this is what our model does. And considering the simplicity of our model, this is already pretty impressive reproduction. There's one parameter which is extremely important. How does A3, so one of the modes, correlate with the actuation? So if you get the phase relationships wrong, of course, your model will have to be poor. The dashed line corresponds to the model, and the solid line here corresponds to the original run starter. Now we look at the lift, and when we turn the lift coefficient over the time, we turn the actuation on, and the lift increases. We see already the high frequency signature here. Then we stop actuation, and then it goes down, and then we see the fluctuation of von Karman vortex shedding. If we fit the lift coefficient with some expansion, we get a reasonably good reproduction. The dashed lines are what the model predicts, and the solid lines are what the runs predict. So what did we learn? Well, we learned a general lesson. And what we would like to do, we have the mean flow with a vortex. We would like to shift it into the direction of the potential flow. Unfortunately, we cannot do it. So what we are now doing, we have to play with the natural dynamics. We just use another fluctuation to change the base flow. We are changed Reynolds stresses. So we go somewhere close to the base flow. And since we cannot control the the von Karman vortex structures directly, we support the enemy of our enemy, and this is a strategy. So often you cannot kill the structures which you want to kill. I can give you many examples of this, but it's always easy to excite a structure, and then you have to excite the right structures, so the enemy of your enemy. And what are the implications of control? Well, let's look at our two oscillator model, so we call it generalized mean field model again, and we put in some numbers, so it's always the small quantities are 0.1. First frequency is 1, and we have high frequency forcing, so we call it 10. And we just look at one growth rate, so this growth rate is positive, damped here. Now, what we would like to do, we would like to mitigate the fluctuation energy von Karman vortex shedding and penalize our actuation. And the first idea which comes to mind, okay, let's do linear control. Let's linearize. If you linearize, you get 1.01. So these terms are missing. So the second oscillator is stable. Your control does not need to do anything, and the first oscillator cannot be affected. And that means linear control, the first oscillator is uncontrollable in linear control. You can only control it if you understand a bit of the nonlinearity. And of course, you know what you need to do. You need to excite the second oscillator above a certain threshold, 0.1, to have a negative growth rate here. So this is your understanding, which you have to bring in order to make control approaches work. Good. So the general approach, just a recap, you have a steady solution, base flow deformation, a component from unsteady vortex shedding from your actuation. So these are the two frequencies. First frequency, second frequency, you always need two modes. Each of the contribution has one corresponding shift mode, Reynolds stress contribution. So you always end up with 6 modes, and you can show that the general structure of the dynamics derived from harmonic balances and so on looks something like that. So we have, I will not go into much detail. You can now do the control design. You only have to focus on the growth rate of the first oscillator, which we have seen already earlier. You can do energy-based control, so you can make the ansatz B. You want to destabilize the second oscillator, so that you can make this ansatz, and you can say the fluctuation level has to be on a certain level. So you can want to identify this function as F, and you can do so from energy-based control. Long story short, I have identified this in a thing for the D-shaped body, where we have another frequency, and we have applied a corresponding control scheme, and it has worked reasonably well. Now, for the dynamical system, what we have here, without forcing, this is the first oscillator, A1, A2, A5. So you have the limit cycle here. On the second oscillator, you are at 0. Now, the transient from the steady solution here to the limit cycle, you start your actuation, you spiral backwards, and here you spiral outwards on the limit cycle, and this oscillator kills that oscillator, and you can see it more directly if you look at the two shift modes. So A5 is the amplitude associated with the first oscillator, and A6 is the amplitude associated with the unstable oscillator. So what you are doing here, you start here, natural shedding, and then you ramp up the fluctuation energy in the first, and have a certain change in the shift mode. You go up here, then you stop actuation, and then you go somewhere here. So this is what you get from your dynamical system. Why are we talking this? There are many examples which fall in this category. So there's high frequency forcing, which Ari Glaser is frequently talking about. There's low frequency forcing and so on. They can all be described in this framework. So one was the D-shaped body, high lift configuration, and I could add many more examples here. So the mechanisms which we have learned now for stabilizing an instability may be encapsulated in this model here. We have one component from Karman vortex shedding, another component could be low or high frequency shedding, and we have a base flow variation. Some forcing may be able to directly communicate with the first oscillator, and then we have to do phasor control. So what we have seen in the first example or in the numerical example. In some strategy we cannot do this, then we have to excite the second oscillator. So we have to use some open loop frequency crosstalk to kill the first oscillator. So it's a destabilizing control using frequency crosstalk. And what I did not discuss, because it's so easy, what you can also do, you can blow the instability away. So you can take, for instance, the D-shaped body, you can make your core undersurfaces, there you simply blow, and you blow the wake away, and you prevent vortex shedding. So in terms of the model, this would correspond for changing the mean flow, and thereby the unstable dynamic becomes a stable dynamic. So these are several strategies of taming and instability. Now there are many more things. So if you look in the literature, you find constant forcing, periodic forcing, opposition control. So we have seen it for the turbulent boundary layer, phase and frequency crosstalk. So this is essentially implicit. You typically have single input, single output. This is the effective mechanism. But there are many opportunities for multiple input, multiple output control. For instance, it's often found that if you use multiple frequencies, it's better than using a single frequency. How are you going to optimize those? Then at some point you may be curious. Okay, you have you do not only want to have multi-frequency, but you also want to have some sensor signal. Maybe you also want to incorporate noise. So this is a general idea of a controller which you get from the literature. And the next thing is maybe you want an automatic identification of the frequency crosstalk mechanism, automatic actuator selection, automatic sensor selection. So this looks like a big fantasy which can never be realized in any practical terms, but it turns out the solution is amazingly simple. And this is what I will talk now. Other questions so far? There were not, let's say, 6 modes, yes. Well, you can take the first 2 modes are POD, the second 2 modes are POD, and the other the shift modes need to be identified in a different method. These are empirical modes, yes, and they are effectively a POD mode if you look at the right transient, if you process them in the right way. Good question. So from your experience. So this is the starting point.
So maybe a bit in the same line. In other configurations, how much? I mean, you will also need to reuse your experience. This is okay, it's a way, but let's say you control a completely different problem. I don't know, a liquid film flow or
yes.